Welcome back to this class, Thermodynamics. In our previous discussion, we talked about the first law of thermodynamics. You know about the thermodynamic processes, and we also talk about the change in the internal energy of a system, and we also talk about the direction of the thermodynamic processes. In this lesson, we'll be talking about heat engine. And again, with me in this course is Dr. Jonathan P. Manigo. In our time, we are familiar and exposed to heat engines. Heat engine is any mechanical device which has the ability of transforming part or portion of the heat energy introduced or given to this engine into some mechanical energy or some mechanical work in particular. And the common example of these devices or engines are our automobiles or car engines. Car industry for a long time has been driven with heat engines. But of course, with recent technology, some which are purely running on electricity and some are also running purely on internal generation mechanism. But for the simple concept of mechanical heat engine, this is a cyclic process. Example, a steam turbine. The primary matter used for the cyclic process is the water, where there is a liquid form of water and converted into its gaseous form, making the turbine to rotate and therefore enable the car transmission to rotate its wheel system. And the process of making this engine operational is trying to maintain its internal energy, by which the change of internal energy would always be equal to zero. Because if the internal energy of a steam engine would change over time, then it would mean that the engine will stop working. So for a good engine, a performing heat engine, its change in internal energy should always be equal to zero. But it does not mean that the engine is not using or releasing any form of energy. It's just that the amount of heat being given to the system would always be equal to the work done by the system. So the working substance for a heat engine may vary depending on the application and the source of the working substance or matter. For these are designed specifically for a specific design of engine. There are engines which requires gasoline, there are engines which requires diesel, and there are engines which requires steam. But the concept is just to provide a mechanism for the cyclic process to occur or happen within a specific type of a heat engine. The concept of heat engines is just a simple mechanism by which you have a source of heat, source of energy. We call it hot reservoir with some temperature TH, which is the source of the amount of heat or the quality of the quantity of heat from the hotter region, which will be converted or utilized by the engine. For this particular illustration, we have the engine in a circle shape. This represents the engine, where this circle or the engine or the device which performs the heat engine mechanism would separate this amount of energy or this heat into two forms. One form is, of course, the mechanical work that this engine is doing to deliver its job, and some of this heat or energy will be converted or discarded into some other form. And the usual scenario where we experience the conversion of this energy from hot region to its working mechanism is our engines in our motorcycles or automobiles, which part of it is converted into the gear mechanism, the working mechanism of the gears of the engine, and some is converted into some form of sound waves. Those are discarded energy. And the most obvious conversion of energy is the heat which is dissipated around the engine towards its environment. So this mechanism of conversion of the heat energy given or introduced into the heat engine will always be conserved. So this is just the mathematical representation of the two, where in reality, the amount of heat which are discarded into the environment or the cold reservoir, mathematically that is in a negative notation. So the net work done by or on the engine per cycle is just equal to the amount of heat the engine is using from the amount of heat given by the hot reservoir less the amount of heat absorbed by the cold reservoir. So the total input of heat given or introduced into the engine would always be equal to the output heat or energy delivered by the engine through its work and absorbed by the environment. And this is the cyclic process. There is some amount of energy given to the engine from the hot reservoir, and some is converted into mechanical work, and some is converted or delivered towards the cold reservoir. And because of this separation of the work delivered by the engine and the amount of heat being absorbed by the cold reservoir, there is this very important performance of the engine being measured, and that is the thermal efficiency, which is also related to the mechanical efficiency of a heat engine. This thermal efficiency is a measure of how good the engine works. This is the ability of the engine to deliver a mechanical work relative to the amount of heat it is absorbing from the hot reservoir and the amount of heat which are discarded towards the cold reservoir. And this efficiency, this thermal efficiency or engine mechanical efficiency, is just the ratio between the actual work done by the engine over the amount of energy given by or taken from the hot reservoir. And if you want to look into it in a percent of in percent form, then you simply multiply this one by 100%. This can also be calculated by just adding 1 from the ratio between the amount of heat expelled to the cold reservoir over the amount of heat being absorbed by the whole process or from the hot reservoir. Our body can also be treated as some kind of a heat engine, though our body operates in a very complicated mechanism. But we can take some concept of heat engine as our body operates. We take some source of energy which are later converted into usable energy form for our body to function, such as muscle work. In the process, not all of the energy contained from our food or drinks will be converted into mechanical or usable work. Most of these energies are converted into waste some in a form of our sweat, some in a form of urine and stool. Our body also is dissipating or discarding energies which are not converted into mechanical work. As an example, we will analyze how the heat engine converts and process energy and how this cycle occurs, or how this cyclic process behaves over time. So let us consider a simple gasoline engine in a large truck which takes in an amount of heat of 10,000 joules and delivers only 2,000 joules of useful mechanical work per cycle. And the heat is obtained by burning this matter. This is gasoline for this case because the engine is gasoline engine. So with this kind of gasoline, its heat of combustion is given to be 5 times 10 to the power of 7 joules per kilogram. For a kilogram of this kind of gasoline, it would require 5 times 10 to the power of 7 joules for it to be fully burned. So we have the following points or questions to answer. First, what is the thermal efficiency of this engine? Second, how much heat is discarded per cycle? Third, if the engine goes 25 cycles, or if the engine works 25 times per second, what is the power output of this engine in terms of watts and in terms of horsepower or HP? Then, how much gasoline is burned in each cycle? And lastly, how much gasoline is burned per second and per hour? So let us solve these particular questions. So we have this direction of heat. So we have the source where the engine takes in 10,000 joules of energy, and the engine processes this energy, converting 2,000 joules into work and giving off to the cold reservoir portion of this 10,000 joules. So for letter A, from the equation given, we can solve for the efficiency of the engine to be just the ratio between the actual work done by the engine and the total energy given off by the hot reservoir. For this case, we have the 2,000 joules being used by the engine in doing its actual work over the 10,000 joules, which is the amount of heat delivered into the system. So with that, it is easily solved that the efficiency of the engine is 0.2, or simply that's 20%. Now, this 20% efficiency of the engine would mean there are a lot of energy which is being discarded into the cold reservoir. So for letter B, we are asked to solve for this amount of energy being discarded into the reservoir. So we have this equation that the total work done by the engine is just the sum of the total energy from the hot reservoir and the sum of energy given off to the cold reservoir. And simplifying this equation, we get the equation for the amount of heat given off to the cold reservoir. That is just the difference between the work done and the heat from the hot reservoir. That is, we have this 8,000 joules. And it is said that the engine goes 25 cycles per second. That means in every second, the engine is able to do 25 works. It performs 25 work per second. And remember that the power is expressed as the amount of work done over how long this work is being done. So we have the power which is just equal to work over time. And since we are given with the frequency, the amount of work being performed by the heat engine in every second, then we can solve for the time. That is 1 divided by 25 works or cycles per second. That is 25 cycles per second, which will give us 0.04 second. Or you can simply divide 1 second by 25. That would give you 0.4 second. So that's the amount of time used by the engine to perform 1 cycle. This will give us the power of the engine to be 50,000 watts, where we have this conversion that for every 746 watts, that is equal to 1 horsepower. Then this will give us that the horsepower of this kind of engine is 67 HP. And alternatively, we can solve this like the power of your engine is just equal to 25 cycles, where in every cycle it requires 2000 joules. This 25 cycles is done in just 1 second. Again, this will give you the same value of 50,000 watts. So now we will try to solve for the amount of gasoline being burned by this engine. So we have the amount of heat given from the hot reservoir, which is the source of the work done by the engine, and some of it is being discarded into the cold reservoir. Since we are given with the heat of combustion of this kind of fuel or this kind of gasoline, we can solve for the mass of the gasoline being burned just to generate 10,000 joules of energy. So we have here the 10,000 joules divided by the heat of combustion of the fuel or the gasoline, which is 5 times 10 to the power of 7 joules per kilogram. And with that, the amount of gasoline required for this kind of engine to generate a heat of 10,000 joules is 0.2 grams. Then, for every 0.2 grams of gasoline per cycle, which is performed by the engine in just 0.04 seconds, the engine used 5 grams of gasoline per second. And converting this to amount of energy for an hour, we have 1 kilogram, which is just equal to 1,000 grams. And for 1 hour, we have 3,600 seconds. Then this will give us 18 kilograms of gasoline per hour. And this 5 grams per second, you can solve this directly by just multiplying 25 cycles divided by 1 second, because we know that the engine is doing 25 cycles per second. Then the same would give you a value of 5 grams per second. And again, the total amount of gasoline being burnt in this kind of engine in 1 hour is 18 kilograms. So with this kind of understanding, you can actually calculate your expenses when it comes to the amount of gasoline your car or your motorcycle or your heat engine in general is using every time you run your engine. Now, the more your engine performs more cycle in 1 second, it would entail more gasoline being burned per second. And eventually, the more you allow your engine to do its work, the more it would require gasoline for it to perform that work. Now again, I mentioned about our body, which can also be treated as a form or a kind of a heat engine. We will now consider this next example, where you think of eating 300 calorie hot fudge sundae with some whipped cream on top. Then to burn this calorie, you run up some flights of stairs to work off this you would be taken. So the question is, how high do you have to climb these stairs? And remember, just like the literal engine, our body is not converting the energies perfectly into usable work. On average, our body is also at around 20% efficient in converting energy into usable work. So if you are around 60 kilograms and with that body thermal efficiency of 20%, we will try to solve this just a serve of hot fudge sundae with whipped cream to ensure that you will not store up this calorie into a form of fat in your body. You need to work off this 300 calorie energy. So the question is, how high? How high? The letter Y here. How high you should be climbing to burn this calorie up. So you have the total amount of energy that is considered to be the energy from the hot reservoir, which is 300 calorie with capital C, which is just equal to 300,000 calorie, or that is just 1,255,800 joules. We have this conversion for every 1 food calorie, capital C is just 1,000 calories, or that is 4,184 joules. Now, from the efficiency given, we can solve for the vertical height which we need to go. And this work that your body would be doing is working against gravity, and that is, you need to gain gravitational potential energy, which is expressed as mgh. I hope you can still remember this one. So from this equation, we can simplify the expression, extracting an expression for Y, and that is just efficiency times the total amount of heat from the hot reservoir divided by mgh. And plugging in values, we get this 427 meters. Just to give you the idea, how high is 427 meters? That is equal to 142-story building. So the next time you would be eating sources of energy, consider your work and how would you burn off this energy that you are taking in. Thank you for listening.